All right, so let's see, let's put everything together and graph a function that we've never graphed before, or a type of function we've never graphed before. We're going to graph f of x is equal to the natural log of x squared plus 9. Okay. So to graph, we're going to follow some points. We know from the derivative, we can tell when where our function is increasing and decreasing. So we're going to do an increasing and decreasing test. With the derivative and the critical numbers, we're going to find the local min and max. And actually, we can use the first derivative test or the second derivative test. It's a matter of preference. And then we're going to look at concavity and inflection points. And then we can add any other points on the graph that we feel necessary, maybe some x-intercepts, y-intercepts, stuff like that. I'll kind of do that as a soft for it. It's not guaranteed. I'm more concerned about those first three, but sometimes the x and y-intercepts are really easy to find. So I'll put that. X, y-intercepts, any extra points, stuff like that. Points as in like ordered pairs. All right, so let's hop to it. So ID test, that means, so increasing, decreasing test, we have to determine the derivative, find the critical numbers, and then look at the intervals that are positive and negative. All right, so take this derivative, it's the chain rule. So derivative of the outside function times the derivative of the inside function. Okay, and now we're going to want to find the critical numbers. So again, that's when the derivative is 0 or undefined. So in this case, we have a rational expression. So there could be some undefined values because we don't want the denominator to be 0. So to figure out in this particular case the critical numbers, f prime of x equals 0 when the numerator is 0. All right, so that's going to give us one critical number, and that critical number is 0. All right, so there's our first critical number. F prime of x is undefined when the denominator is 0. All right, and then actually x squared plus 9 is never 0, right? If we solve this, we get x squared equals -9. That's not possible. And also, if we were to graph it, this is a parabola with a vertical shift of 9. And we could see it never reaches the 0. All right, so it's not undefined. So we have one critical number, and that's x equals 0. Okay, so let's come down here. And remember, always label your graphs. This is our f prime. And we'll see if our test points are positive or negative. Okay, so where's our f prime? So let me just rewrite it. So we have it right here. And the denominator is always positive. Okay, because x squared is always positive plus a positive number is always positive. So I'm just counting factors. So the numerator is going to determine if the derivative is positive or negative. So let's do our test points. So if we're over here and it's like -1, right, to the left of 0, 2 times -1 is negative. So the whole function's negative. And then to the right, let's do another test point like 1. 2 times 1 is 1, so that's positive, and the denominator is positive. So that means our derivative is positive from 0 to infinity. Okay, so the increasing decreasing test told us that f is decreasing where the derivative is negative. So this interval right here, -infinity to 0. And the increasing decreasing test the ID test, told us that we're increasing when the derivative is positive, so 0 to infinity. All right, so lovely. We can also run the first derivative test right now. That's the second thing we do to find the local mins and local maxes. Okay, and we can do that using the first derivative and the critical values. So look at right here. At 0, so 0 is going to be, local min or local max because we have a sign change. F is decreasing before 0, and then after 0, we're increasing. So is that going to be a local min or local max? It's going to be a minimum value. So we're going to have a local min, this is by the first derivative test, at 0, f of 0. Okay, and do you remember what f is? It's this crazy function, right? Natural log of x squared plus 9. I'll rewrite it. So at 9, or at 0, it's going to be the natural log of 9. That's a calculator part, because I don't know how to graph natural log of 9. So I went to my calculator, and I saw that the natural log of 9 was about 2.2. Okay, I'm not going to get too accurate because I'm just, grading with my own tick mark system. But, you can get as accurate as you want depending on what your scale is on your graph. But I'm just going to go like to the nearest tenth. Okay, so the last thing we're going to need is the concavity, and that's the second derivative test. So our, where is it? Here it is. 2x over x squared plus 9. Let me write it down here. We have to find the double derivative. So we have to take the derivative again, because concavity deals with the double derivative. All right, so it's the quotient rule. Let's take the derivative of the top. All right, and then we take the derivative of the bottom. Happens to be 2x. And then divided by the bottom squared. Okay, so let's clean it up. Okay, so what is that? Negative 2x squared plus 18. Okay, and then there you go. We can leave it at that. All right, so now we're interested in the critical numbers, or where f double prime is 0. Okay. Well, let's see. F double prime is 0. Not when the denominator is 0. That's when it's undefined. Remember, the denominator can't be 0 because x squared plus 9 is always positive. So we want to figure out when negative 2x squared plus 18 is equal to 0. All right, so let's solve this. You can add 2x squared to both sides. Divide by 2. So this is a quadratic, right, with no middle term, so I'm inching my way towards the square root property. All right, take the square root of both sides and add the plus or minus. Okay, so there we go. So on our double derivative, remember, always label your number lines because we're dealing with a lot of different functions, or derivatives of the function. And wherever the double derivative is negative, it's concave downward. And wherever it's positive, it's concave upward. All right, so this is our double derivative. The bottom's always positive. So really it's whatever the top is. If the top is negative, the function's negative. If it's positive, the double derivative is positive. So let's do our little test points. Let's do -4, for instance. That's going to, let's see, this is going to be 16 times -2 is -32 plus 18, still negative. Okay? When we plug in a 0 for the test point, our favorite test point, we get 18 in the numerator. And then another test point is 4. And same thing, right? We would get the same number as before. It'd still be negative. Okay, so it's the double derivative. See why it's so important to keep track? So we just determined where we're concave downward. From -infinity to -3, and from 3 to infinity. And then we're concave upward from -3 to 3. Okay? And because there's a change in sign of the double derivative, we have 2 inflection points. At -3 and 3. Okay? So we have to go all the way back up to our original function to figure out where they occur on the f graph. Because that's what we're trying to do. We're trying to graph that original function f. Okay, so it's going to be -3 times the natural log of x squared plus 9. Whew. Okay, so again, figuring out that function value, that's definitely a calculator problem. And they're actually the same, right? Because -3 squared is the same as 3 squared. So we have inflection points at plus or minus 3, and the calculator tells us that that's about 2.9. Okay, so let's put all of these pieces together, and we're ready to graph now. So we're going to use all of these pieces to graph this crazy function, right? And remember, the function is the natural log of x squared plus 9. Okay, so notice that we're kind of hovering. Let's just scan back a little bit. We have increasing, decreasing. Okay, so our local min is at 2.2. And then we have these inflection points at 2.9. So the vertical spread isn't that much. So I'm not going to make it that high up. All right, so maybe 1, 2, 3, and then everywhere in between. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Whoops, I got one as 11, but we'll just pretend that didn't happen. There we go. Okay, so first things first, we know we're increasing here. So I'll just write these in a lighter tone. So we're increasing from 0 to infinity. So I'm just kind of bringing all the information here. We're decreasing over yonder. We discovered that in part 1. Okay, what else do we know? We know that the local min happens at 0, 2.2. That's what we got from part 2. And then part 3, we have some inflection points. Let's do 1, 2, 3, 1, 2, 3. At 3 and -3. Those are our inflection points, where the concavity changes. All right, and then final thing is where we're concave up and down, and we're, let's see, concave down. I just like to write little notes so I don't get confused. on the outer edges, and then in the inside, we're concave up. So just little notes to myself so I can sketch a nice graph. So let's start putting everything together. Our minimum value is 0 and 2.2, somewhere around there. 3 and 2.9 are the inflection points. We have some nice symmetry. It's an even function. Okay, I think that's pretty much even. Okay, and then we're decreasing here. So our graph is going to go downward to the left of 0, and then we're increasing to the right of 0. So we're going to go right. And then in between the inflection points, we're concave down. Okay, and we are an even function because, again, all of our exponents are even. This is scary. So we're concave down here. Okay, between the inflection points, increasing to decreasing. And then after the inflection point, the curvature changes, and we're going to do more of a sad face, right? So like that off to infinity. And there you go. That was a crazy graph, but we were able to graph it using only derivatives.